Hello, and welcome to today's webinar entitled A Dual Tracer Approach to Measure the Effects of Exercise on Energy Expenditure and de novo lipogenesis during weight regain. I will be serving as your moderator today. My name is Dr. Damian Romero. I am the chair of the American Physiological Society's Endocrinology and Metabolism section and a professor at the University of Mississippi Medical Center. In today's session, Dr. Paul Mclean will discuss his research on the effects of regular exercise on energy expenditure and nutrient trafficking during weight regain after weight loss through the use of tracers and metabolic phenotyping. I would like to thank our sponsor, Columbus Instruments, for working with APS to spotlight impactful and exciting science. A few housekeeping notes. Out of respect for our speakers, we ask that you refrain from photo or video captures of the presentations, in whole or in part. This session will be recorded and available for future viewing through the link on the registration website. Recording or taking photographs of another person's presentations without their explicit permission is prohibited. At this time, all attendees except for the speakers are in listen-only mode and with video off. As moderator, I will be happy to raise questions that are typed into the chat. You may put your questions in the chat at any time. The session will end at approximately 12:15 p.m. Eastern Time. It is now my great pleasure to introduce our speaker, Dr. Paul Mclean. Paul Mclean, PhD, is a professor of medicine and pathology at the University of Colorado School of Medicine, with 25 years of experience studying obesity and its metabolic complications. He is the director of the Colorado Nutrition Obesity Research Center and the director of Research and Education Integration from the Anschutz Health and Wellness Center. Welcome, Dr. Mclean.
Thank you, Damien, for that introduction, and thank you to Jacob White and Chris Adams for putting this together. It's certainly a pleasure to be here and have the opportunity to talk to you about our research. I'm going to highlight some of the uses that we have had for metabolic phenotyping systems and tracers today, as we have applied them to further our understanding of how exercise affects weight regain and how it can be used as a strategy for weight loss maintenance. So I'm going to turn my video off so that you can focus on the presentation now. My laboratory studies the problem of obesity, and this is a big problem in the United States. Over 2/3 of adults are afflicted with overweight or obesity, and this incidence is higher in higher in women and minorities, and we're definitely passing this along to the next generation. And this is a big deal because obesity affects almost every organ in the body in a pathological way, and this leads to a very high healthcare cost. But beyond that, obesity is affecting the way that we live. It's affecting how we function, and it's reducing our quality of life. So this is a big problem in society, and because it's a big problem, we have developed a lot of programs, diets, books, and exercise interventions that help us lose weight. And these programs generally work. This is just looking at weight loss with 4 different dietary interventions. And programs, when people get on them, they generally help people lose weight. But the problem is that the people go off of their programs fairly early and back. This is a meta-analysis of US weight loss studies looking at the percent of lost weight that is regained in the years following a structured weight loss program. A lot of the weight comes back early on, and most, if not all, eventually returns. So this has turned out, this problem of weight regain has turned out to be one of the biggest problems that we've had in successful in obesity therapeutics. So why do we regain the weight? Well, there's been a number of factors that have been proposed over the years, and over a decade ago, the literature was quite confusing with all the different types of explanations that came that were put forth as to why this is a problem. Well, today I'm going to try to provide some clarity in order to lay the foundation for some of the studies I'm going to show you. I'm going to provide clarity to that question of why we regain weight and talk about the barriers to successful weight loss maintenance and use that as the foundation for why we were interested in exercise and using metabolic phenotyping systems to understand exercise as a strategy for weight loss maintenance. And then I'll end on a tracer approach that we have applied to further our understanding of exercise and why we believe exercise is critical in a weight loss maintenance regimen. So to begin with that question, why do we regain weight? In 2014, I led an NIH working group entitled Innovative Research for Weight Loss Maintenance. And this was done in collaboration with Rena Wing and a number of different NIH institutes and centers. We gathered a panel, a broad panel, different scientists from a number of different disciplines, and we asked them to address two issues. First, what are the barriers to successful weight loss maintenance? Particularly take that confusing literature and give us some structure to it so that we can address it more systematically. And then answer the question, what are the challenges of developing better treatments? Well, they came up with three barriers. And the first is that there's a strong biological drive to regain weight. There are adaptations in the brain and peripheral tissues and critical neural and peripheral regulatory nodes that are involved in the homeostatic system that controls body weight. These adaptations, physiological adaptations, culminate in an elevated appetite and suppressed energy expenditures, suppressed metabolic requirements. These adaptations are strong, they're coordinated in a number of different tissues. They regulate both sides of the energy balance equation. They prepare peripheral tissues to take up and store energy in a very energetically efficient manner. These adaptations may extend to the hedonic aspects of food intake, and they may extend to the motivation to be physically active. We know these adaptations are fairly persistent. They don't appear to resolve with time in most of our preclinical models anyway. The second barrier has to do with a very predictable decline in adherence to the behavioral programs. This happens between 3 and 9 months of a weight loss program. It coincides with the weight plateau that many people who are losing weight experience. The problem is this is gradual, it's intermittent, it's very difficult to study. The root origins of this are very complex and multifactorial. They may have to do with people viewing their weight loss strategies as transient endeavors, or the perceived cost-benefit ratio might change when they're having to do the same amount of work just to maintain their weight loss rather than seeing any weight loss. Boredom or aversion to the program that they're on, or returning to entrenched eating or inactivity habits. And of course, that strengthening biological drive. The third barrier has to do with our environment. And this has to do with food availability and security, socioeconomic status, the cultural demands of our friends and family, and the built environment where we live, in our homes, our neighborhoods, and at work. That idea that this is so pervasive and so persistent that this pressure from our environment makes maintaining weight loss so difficult. So the barriers to successful weight loss maintenance are in our biology, our behavior, and our environment. And we are all different people, and that yields a lot of individual variability in these three pressures that are affecting body weight. And the consequence to that is that there's a lot of individual variability in the response to obesity treatments. And it doesn't matter whether it's a pharmacotherapy drug or diet, surgery, and what we'll talk about today, exercise, we see individual variability in the response to treatments. So exercise, here's an example of that individual variability. This is a 6-month supervised exercise intervention from Joe Donnelly's group. You can see with 16 months of exercise, some people lose weight, some people gain weight. Men tend to do a little bit better than women in this study. But this is reflective of a number of different studies that have shown, on average, if you average this out, exercise is not that effective on its own for weight loss. But what about weight maintenance after weight loss? Well, there's some data from the National Weight Control Registry that showed that people who are successful in keeping the weight off, 80 to 90% of these people include regular exercise in their weight loss regimen. And there's a number of other studies that would suggest that exercise is important. The problem is when you go to clinical trials, at face value, a number of clinical trials would show that there's very minimal or little benefit, if anything. And Rebecca Forwhite, was a graduate student in the lab, and she published a paper that kind of summarized the perspectives that have been percolating in the literature for quite some time. And it's really not about the exercise. When you take a closer look at these clinical trials, it's really about the compliance. Those studies that showed high levels of compliance actually showed benefits of exercise, and those that had problems getting people to comply to the exercise program showed little to no benefit. Well, if you a number of studies have gone back and retrospectively looked at specifically those people who did exercise, and when they did do that, they found, yes, there's an association between actual exercise and weight loss maintenance. So here's a gem of knowledge that you can take home today. In order to get the benefits of an exercise intervention, you actually have to do the exercise. That might be surprising to some of us. Here's some data of one of those reanalyzed clinical trials. This comes from John Jacizek's group, and he showed this in a dose-dependent manner. The more that you exercise, the better you are at keeping the weight off after weight loss. Now, the problem is we can't really get the gold standard randomized clinical trial here. And this has led to some disagreements. The proponents of exercise will say exercise is effective or efficacious for those who do it. But the skeptics would say, well, those who exercise might just be more likely to stay on their diet. And exercise really isn't doing anything per se. It's just along for the ride. And this is where our research has come in. We had a hypothesis that this is not a coincidence. Exercise is actually changing our physiology to have a beneficial effect. And so we had this hypothesis that exercise actually counters those biological adaptations to weight loss that are driving weight regain, those adaptations that I talked about earlier. Now, the problem with testing this hypothesis is it's really difficult to do in humans. And it's because of that individual variability I mentioned in our biology, our behavior, and our environment. It's really hard to control that in humans. And that's why we decided to focus on an animal model of the human condition to ask what specifically exercise was doing to the physiological adaptations to weight loss. So our model that we use is outbred Wistar's. We put them on a high-fat diet, limited physical activity, and we select those animals that gain the most weight. And we call these animals obesity prone. They have a polygenic predisposition for obesity under conditions that we think are important or contributing to the obesity epidemic. We take those animals and we can study them, we mature them, and we put them in a paradigm of weight regain. We get them obese, we put them on we can study them in the obese state, or we can put them on an energy restricted low fat diet and then give them a limited daily provision of that diet to keep them weight reduced over a period of time. And then we model the holidays. We allow them to overeat, eat all they want, and they will overeat and gain the weight back. Now, we can study a number of different things in relation to obesity therapeutics in this paradigm. And to study exercise specifically, we simply keep one group of animals sedentary and we exercise the other group. Now, as much as I would like our animals to lift weights and do strength training in this paradigm, our obese, weight-reduced animals are very much like obese people with obesity who have lost weight. Most of them don't really care for exercise. And so this is a picture of Amy Steig. She was a graduate student from many years ago. And you can see her, she had to become an ardent personal trainer. And here you see her using the Columbus Instruments animal treadmill to train these animals. And we had to use different methods to train these animals and motivate them to become physically active. We were able to get these animals to exercise 60 minutes a day, 6 days a week, 15 meters a minute. And so this equates in human terms, I would say, to a slow morning jog. Now, if you put this exercise intervention in our weight regain paradigm, we find that exercise, this is looking at the percent of lost weight that's regained, exercise reduces the rate of gain early in relapse and lowers the defended body weight and fat mass such that they're defending a lower body weight and fat mass at the same levels of leptin and insulin. So to get an idea of what's happening with energy balance and how exercise is affecting the energy balance equation there, we have to go to metabolic phenotyping systems. And we've, over the years, used the Columbus Instruments Oxymax CLAM system. Really like this system in that it's modular, simple to use, and it's fairly straightforward for our purposes. We worked with Ginger Johnson, who's a managing director of this core for over 2 decades, and brings a lot of expertise to the table for these long-term phenotypic studies. We use cages that have a lot of bells and whistles on them and allow us to measure energy intake, expenditure, spontaneous activity, and fuel utilization with the respiratory exchange ratio. The other benefit of the Columbus system is that we have a metabolic modular treadmill that we can plug into the indirect calorimetry system and measure the exercise energetics. So we can measure, once we start the exercise, we can see how much energy they're expending and the types of fuels that they're using to expend that energy. And in this case, we found that the animals are expending about 2 to 3 kcals, depending upon their body weight. So we can take this data and include it in our energy balance calculations. So what does exercise do? We found if you look at energy balance in lean, obese, and weight reduced, and this is looking at the days of relapse after they're allowed to overfeed, the animals, a sedentary animal has what we call a very large energy gap. And this is really a representation or a manifestation of the biological pressure the animal is experiencing on a day-to-day basis to go off the diet, overfeed, and gain that weight back. This is the difference between intake and expenditure. And you can see that with exercise, appetite is more closely matching the energy requirements. They're still overfeeding, but the exercise is reducing that energy gap by 80%. It's really hard to tell. Most of this can be explained by a reduction in the food intake, but it's really hard to tell what's happening with energy expenditure because the sedentary animals have so much extra energy. They have increased their energy expenditure to pay for that deposition. What about fuel utilization? And this is where the respiratory exchange ratio comes in. This is the ratio of carbon dioxide production to oxygen consumption. The higher the RER, the more carbohydrate oxidation, the lower the RER, the more fat oxidation. And when animals are in energy balance in the weight reduced state, substrate disappearance calculations are fairly reflective of substrate oxidation. So we're fairly certain under these conditions that the animals, that the exercise is promoting an increase in fat oxidation earlier in the day and sparing carbohydrate for use later in the day. The problem with looking at fuel utilization when the animals are overfeeding is that they're now out of energy balance. And the sedentary animals have excess calories that they're depositing. And so de novo lipogenesis, which has its own effects on elevating RER, can come into play. So while we see that there might be an effect on fat oxidation early and late, we really don't know what's happening here, because when the animals are out of energy balance, you can't say that substrate disappearance calculations from the system are equating to substrate oxidation. So this is where we were stuck, and we needed our metabolic phenotyping systems were insufficient for us to understand what was happening in the overfeeding condition, because we had a hypothesis that while animals are overfeeding, they're burning their dietary fat and redirecting other nutrients, carbohydrates and proteins through more energetically expensive pathways. So we had this hypothesis. During weight regain, exercise enhances oxidation of the ingested fat and redirects carbohydrate and protein to more energetically pathways of weight of deposition. And this is rooted in this idea that if you have a caloric load and your body is choosing to store dietary fat or carbohydrate and protein, well, it's relatively cheap and efficient to store dietary fat. The processes, the metabolic processes here to convert that to triglycerides and stored in adipose tissue are relatively inexpensive. The theoretical estimate is that of the caloric load, you might expend 2% of that caloric load to pay for that deposition. It's very different for carbohydrate and protein. You have some very expensive metabolic processes that you have to go through to turn that into fat and store it in adipose tissue. So this is expensive and inefficient weight gain. Theoretical estimates suggest that upwards of 25% of that caloric load would be needed to pay for that energy deposition. So we were thinking if exercise promoted the oxidation of dietary fat, it would favor the storage, this more expensive and efficient weight gain. So in order to test that hypothesis, we really needed to go to tracers. And for that, I relied and joined efforts with Matt Jackman, who's now Associate Director of our Colorado Molecular, Cellular, and Analytical Core. He's shown here in the picture with his wife, Stephanie. He and I have developed a way to look at the net retention and fuel utilization under conditions where animals are overfeeding. And so I want to give him a lot of credit for coming up with the study design and keeping us on track. We were really wanting to know how is weight gained during the relapse process. And I'll just mention that these studies now, the studies I showed you before were on a 12% fat diet. These are more on a medium fat diet to reflect the human condition. And this is the study design. We took those same obese animals, put them through a weight loss program, calorie restricted diet, and we kept some sedentary, we exercised others. And then we put them through a 24-hour dual tracer study. And we looked at groups in the sedentary condition, those that were weight reduced and in energy balance, and those on their first day of relapse when they're overfeeding. And we looked at the same groups in the exercise, with the exercise intervention. Now, we know that this overfeeding group in the sedentary animals, they're going to overfeed a lot more than the exercise group. So we wanted to include a controlled overfeeding group, and we call this a gap matched group. We're essentially matching the positive energy balance that is being experienced, so that both of these groups had to deposit the same amount of energy. Now, with the tracer program, the tracer paradigm, the animals were placed in the metabolic chambers for 3 days, and we had to do this to acclimate them to the chamber and to the modified feeding modality, and to get baseline measures of their intake, expenditure, and to make sure that the animals, particularly the weight-reduced animals, were in energy balance, so that we could calculate how much food to give, particularly in the controlled overfeeding group. We maintained them on their sedentary and exercise regimen. And then we modified the phenotype system to where we were able to collect and trap expired CO2. So with this, we used a push Oxymax clam system, and we paid careful attention to maintaining a fairly good, tight, and sealed program. The line we installed came from the overflow or exhaust port from the cage. And this line we could use a flow meter to look at how intact that system was. And we could time and measure the rates of CO2 trapping. With this line was directed to a ventilated hood and CO2 trapping tubes. Now, here's what the tracer study looks like. We have 2 tracers that we're using. We used the tritiated water injection. This is done intraperitoneally, and we've shown that within 2 hours, this tritiated water becomes equilibrated with body water. And that's important because we want this tritium to be available, this water to be available for metabolic processes that utilize water. And the process that we're most important or we're most focused on here is the incorporation of that tritium into newly formed fatty acids as they are formed through de novo lipogenesis from carbohydrate and protein and get esterified and stored in fat. So that is going to be in the body over the 24-hour period, and that's going to allow us to measure the net retention of de novo derived lipid in lipid pools around the body. The other tracer is the C14 fatty acids, and we incorporated this into the diet in a 3-to-1 ratio of oleate to palmitate, as that was the ratio of the dietary fat, the composition of the diet. And so this was placed in their food, and the animals could eat it all day long. And so the amount of this tracer that went in was reflective of how much food they ate and how much dietary fat they ate. This would be trafficked around the body. We could collect, we could collect CO2, trap the CO2, and see how much of that dietary fat was being oxidized. And it would get retained in tissues. And so we could look at the net retention after 24 hours. Where did that dietary fat go? So the animals were in the chamber. We measured VO2 and VCO2 throughout the subsequent 24-hour period. And we measured food intake and trapped CO2 at 3-hour intervals over that period of time. This allowed us to measure energy balance, fuel utilization, not only with respiratory exchange ratio, but with the dietary fat that was trapped as CO2, and then the net retention of both de novo and dietary fat. So here's the energy balance of the groups that we looked at. You can see the obese animals here. They're eating a lot and expending a lot. And, in the weight reduced state, we have to give them less food to match their lower metabolic requirements. And in the clinic, I think it's important to point out, this is what we really think about in the clinic as being the energy gap that we have to make up. And the idea in the clinic, people are looking, if we could just exercise enough to make up this difference, we would help keep people keep the weight off. But as I showed you in the first study, and I'll show you here in this study, that biological pressure, that energy gap is much greater than I think that we're estimating. These animals overeat to a much greater extent than they did when they were obese. So you can see this is the biological pressure of this animal to go off its diet and overfeed and gain the weight back. So these animals are overfeeding. There's a strong drive to overeat. And on this 25% fat diet, you can see what exercise did. Exercise counters that drive to overeat and essentially cuts that energy gap in half. Well, that's the effect on appetite. How do we get a handle on energy expenditure? And that's where that controlled overfeeding group comes into play. You can see that the sedentary and exercise groups are expending about the same number of calories right now, but the exercise group has about half of the caloric load to deposit over that 24-hour period. To understand what's happening with energy expenditure, we've taken a sedentary animal and we have essentially titrated down overfeeding so that we're matching that positive energy imbalance. We call this group the gap matched group. So they have the same positive energy balance. And when we do that, it turns out we have to feed them 9 kcals less, and because they're expending 9 kcals less. So exercise is increasing energy expenditure, and not all of that can be explained by the cost of the exercise bout that we measured and I showed you earlier. So this is the energy balance of the groups. This is intake minus expenditure. And I want to focus the subsequent slides on these two groups, the exercise and the sedentary group, that are matched for that positive energy imbalance. Now, when we do that, we'll first look at the oxidation of dietary fat. This is the C14 tracer. Even in the weight-reduced state, we see that exercise promotes the oxidation of ingested fat. And remember, these animals are in energy balance, so there's really no difference in 24-hour whole body fat oxidation. But this preference to burn dietary fat persists in relapsing animals, such that the exercise, even though they're eating less, they burn more dietary fat than the overfeeding sedentary group. And not all of this is due to the overfeeding. Some of this, about half of it's due to attenuating the overfeeding, the magnitude of overfeeding, and about half is explained by something else that's going on in the periphery. Well, with that difference in dietary fat oxidation, we expected to see differences in the net retention of how fuels were being stored. And so if you focus just here on the exercise and the sedentary animal, the net retention of dietary fat was reduced in exercised animals. So they're oxidizing more, and less of that dietary fat is getting trafficked to adipose tissue. And more of that dietary fat is ending up in the lipid pools of the liver and skeletal muscle, where it's more likely to be oxidized. In contrast, exercise favored or enhanced the net retention of lipid via de novo lipogenesis. This is the more energetically expensive way to gain weight and deposit this energy. In fact, all of the lipid pools that we measured showed that exercise enriched these lipid pools with de novo derived lipid. So I don't have time to talk about it today because just to let you know that we've had a number of follow-up studies from these tracer experiments that have molecularly profiled, whether it be gene arrays, RNA-seq, and Western blotting, to look at the adaptive responses in skeletal muscle, adipose tissue, and the liver that are consistent with this shift in fuel utilization that I just talked about. Here are the general adaptations to weight loss that are promoting rapid and efficient weight gain. And I won't go through them specifically, but what we've published over the last decade in a series of papers is that exercise in this context enhances the oxidation or the capacity to take up an oxidized fat, increases mitochondrial content. It reduces the lipogenic capacity of adipose tissue, so reduces the capacity to take up and store fat in adipose tissue. But surprisingly, it enhances the lipogenic capacity of the liver. Now, with these molecular profiles that we've published over the years and our tracer data, we can come up with an overall picture of what exercise is doing to peripheral nutrient trafficking and how it's affecting the weight regain process. So with sedentary rats, they're eating a lot and they're expending very little. And so there's a lot of calories that are coming in that need to be stored. And what the body does is it traffics dietary fat to adipose tissue. And it preferentially uses carbohydrate and protein for its energy needs. So this is a very efficient way to deposit excess energy, and it hastens the dissipation of carbohydrate very efficiently. If there's excess carbohydrate or protein, it can go to fill up the glycogen stores, but that also excess energy can go directly to adipose tissue where de novo lipogenesis can occur, or it can be directed through hepatic de novo lipogenesis and eventually end its way to being deposited in adipose tissue. So overall, this is a very rapid and efficient way, energy efficient way of depositing energy. So what happens with exercise? Well, number one, they're eating less. And so you have a lower caloric load, but there's a retrafficking of dietary fat because of the molecular changes in adipose tissue and skeletal muscle. The dietary fat now is being re-trafficked to oxidative pathways, skeletal muscle, and it's being used for energy and to the lipid pools in the liver. And less is going and getting deposited directly into adipose tissue. And this leads to the retrafficking of carbohydrate. The carbohydrate and protein can go, instead of being oxidized, filling up glycogen stores and really being trafficked through hepatic de novo lipogenesis rather than going directly to adipose tissue. Now, we think this is important for two reasons. The first is that this excess energy now has a second pass at oxidative tissues before it gets deposited in adipose tissue. That's number one. But I think the more important point here is that this is energetically expensive deposition, and it is what we think this increase in energy cost for depositing this excess energy. That, in combination with the cost of the exercise bout, is why we're seeing that attenuated decline in energy expenditure. It's essentially explaining the energy expenditure we see with exercise. Now, what I haven't talked to you about is what's happening with appetite. That's a story for another day. I think that there's a lot of studies going on how exercise is affecting the appetite side of the energy balance equation. Okay, so reflections on the tracer approach. You know, we really have there's a lot of advantages with using the OxyMax system in combination with these tracers. We can look at the assessment of energy balance, fuel utilization, and excess nutrient deposition, essentially looking at how nutrients are trafficked and stored in the context of overfeeding. And so we've applied this approach to our studies of obesity and overfeeding in breast cancer models. And we have applied it in looking at maternal obesity and its effects, how nutrients are trafficked from the mother to her litter, in rodents. We can look at the trafficking, oxidation, and retention of nutrients in how maternal obesity is affecting early life programming. So we've applied it in a number of different contexts. The limitations, there are logistical challenges. We like to use radioactivity because the radioactivities, the tracers are very sensitive. We get very rapid measures. They're easy to use. Scintillation counter is all you need. But there are regulatory approvals, and we have to be careful about our environment being very clean and being meticulous to keep the laboratory environment clean, because these animal studies can be kind of messy. Doing a 24-hour study, myself and graduate students and postdocs, we have to stay overnight in the lab. So that's one of the limitations that I think we all don't appreciate. The modifications to the phenotyping equipment, you do need to know a little bit about how these systems work before you start tweaking with them. And the good thing with the Oxymax system is it's relatively straightforward and it's modular. And we know enough about the system to modify them and have our checks and balances in place to be confident with what we're measuring. The last thing I'll say is overfeeding by its very nature is a non-steady state condition. And so this is not like a lot of tracer applications where they're establishing a steady state and getting a measure of rates. We're looking at net retention or picture at specific time points and net retention over the 24-hour period without any kind of knowledge of how those nutrients were trafficked or between tissues. And so other types of studies are going to be needed for measuring tissue-specific rates of de novo lipogenesis, for example. So finally, I'll end on an overall summary of the science, and that is, we believe that exercise is critical for successful weight loss maintenance. Despite the fact that we can't really get good randomized clinical trials, we believe that exercise is countering those biological adaptations that are driving weight regain. We see in our animal models that exercise suppresses appetite. It increases energy expenditure above and beyond the cost of the exercise bout, and it essentially makes weight gain energetically expensive. So somebody who's relapsing and who's exercising, the weight that's gained, it costs more to put the weight back on. Now, the last point I'll make is an important one. I haven't really had time today to talk about this, but there are clear sex-specific differences with the effects of exercise and the biological drive to regain weight. We've published a series of papers that have shown this. The benefits, most of the data that I showed you today is from males. And the benefits in this paradigm, or at least in these animal models, show that the exercise benefits are more apparent in males than in females. And so important to keep that in mind. So with that, I'll acknowledge a large group of people who have been involved over the past decade. Matt Jackman and Ginger Johnson, I mentioned before, and Rebecca, who published that paper. And I just want to point out Janine Higgins, who was involved from the very early days in designing these studies. We have a number of these people who are graduate students or postdocs and moved on to now postdoctoral fellowships or their own faculty positions and building their own research lab. But over the years, they were involved in the molecular profiling of the tissues. We have some great collaborators with at the Anschutz Health and Wellness Center, and of course, the funding support over the years to support these studies. And also a brief thank you to NIH and a number of the different institutes and centers who have kept the workshop that I mentioned, kept that going over the last few years, and it has developed into what's now called the Adopt Core Measures project that continues to this day. So I'll end there and I'll come back on. I'm happy to take any questions.
Thank you so much, Dr. Mclean. It was really a fascinating talk. So now we're going to open the presentation for questions. So invite the audience, to place the questions in the Q&A section. We already have a bunch of questions, very, very exciting presentation. So I think I'm going to begin to read some of them. We have questions like, for example, it says the exercise regime is likely to cause an alteration in the lean fat mass ratio. Is that taken into account to explain these potential beneficial effects of exercise?
So if I understood the question correctly, we do body composition measurements, and in our studies, the animals don't lose much lean mass. Most of what they're losing in the weight loss has to do with a loss in adipose tissue. And our exercise itself is not really intense enough to increase lean mass over the times that we're treating. Here, I'm gonna stop sharing so that we can talk. So what we're seeing in relapsing animals is a relatively stable lean mass. They lose a little bit and they gain a little bit during relapse. And I'm not quite sure if that answers the question.
Yeah, no, thank you so much. Another question, I think related to that, the intensity of the exercise is the ability of exercise to limit the reduction in energy expenditure depending on the intensity of the exercise?
Yeah, it's a really good question. We'd really like to answer that question. It's hard to, these weight reduced rats really don't like the physical activity. And so it's really hard to get them to increase their intensity. They're not like humans, so where we can take them into the clinic and they're motivated to be physically active. And so we haven't done a lot of studies on intensity. We've toyed with the idea of doing different modalities where we could increase the intensity and do more of a strength training intervention. But we just really haven't done those studies yet.
Okay, thank you. Well, of course, you can imagine a lot of people praising your presentation. Everybody amazed of your exciting results. One of the questions says, could you also show that the fat is actually oxidized in the muscle and liver of the exercise mice? And also, do you think that there's a risk in this change in the direction of the fat utilization on ectopic fat deposition?
So it's a good question. And, we were concerned if we were seeing an increase in hepatic de novo lipogenesis, were we actually creating, a fatty liver in the process. We were, with this retrafficking of nutrients. And we don't see hepatic steatosis or the accumulation of lipid in the liver. Under these conditions, it looks like the lipid is being trafficked to the liver, but being packaged as VLDL and secreted out. And so we don't necessarily see under the exercised condition a problem with ectopic lipid accumulation. Now, there's a caveat to that. We have done studies where we have stopped exercise while the animals are refeeding. And when we stop the exercise, and exercise, it's essentially exercise cessation, now the liver is very primed for hepatic lipid accumulation, and they do develop a very severe steatosis in the liver. So the message that we have from our animal models is don't stop exercising, particularly during weight regain, because there could be very bad metabolic effects. And I think John Tifo from Kansas has studied exercise cessation and has shown some consistent observations of what exercise cessation can prime the liver to do.
Thanks so much. I mean, I think that with the question it's getting even more and more exciting. So probably we had to follow all this in the future. Because super exciting. Yeah, because I think you were like even thinking of the question that were coming in advance, because some people were asking about what happened. Yes, if you follow these animals over time, if these metabolic changes, remain for a long time, or.
So yeah, we have published a paper, it was probably back in 2004, 2006 or something like that, where we maintained the weight reduced state. We took them upwards of 16 weeks out to see if these metabolic adaptations would dissipate or go away. And they did not. In fact, the longer that we kept the animals' weight reduced, the stronger that drive became to overeat and regain the weight back. It was almost like the animals had a weight trajectory, a hypothetical weight trajectory that was increasing over time, and their bodies knew where that was. And when we finally allowed them to overfeed, they would overfeed a lot and increase their weight gain, the rate of weight gain, and kind of a depressing message. But from our perspective in our animal models, it doesn't dissipate. Now, there's some clinical studies that would suggest that people can use behavioral strategies to overcome those biological pressures, and that weight regain or weight loss maintenance can become easier over time, just as people implement behavior change programs and different strategies to counter those biological pressures. So maybe that's a positive message.
Yes, another question, regarding this, perhaps not following the animals to older age, no, but related, you show exciting results with 24-hour studies with the metabolic tracing. Have you performed longer studies? Is feasible? We already applaud you for doing 24 hours, okay, but
Yeah, so we could do, a 24-hour experiment is really good because it gives us a block of time of energy balance, where we can say, over this 24 hours, here's what they ate, here's what they expended, and here's what is happening with nutrient trafficking and retention. You could reasonably do a tracer study over a 3-day period, but the tritiated water or deuterated water, if you use that, is going to dissipate over time. And so we really like the 24-hour block. It would make more sense for us that if we wanted to know what was going on during the relapse process, that we do 24-hour tracer studies at specific times as the animals are relapsing.
Yes, excellent. Thank you so much. And I think also in the last minute of your presentation, you opened the Pandora box, mentioning these different sex differences. So a lot of people, as you can imagine, asking if you can at least comment on this, to give some hints. People are very excited about this topic.
I have to say, when I talk about this with my wife, this is the most depressing aspect of my research. What happens with females is that they exercise, and what it looks like is that they are able to sense that extra energy that they need for the exercise, and they increase their food intake to match what the exercise is doing. And the weight regain curves are, overlapping. Exercise, the same sort of exercise intervention that we do in the females, it doesn't do anything to the weight regain process. The animals will relapse just the same as a sedentary animal. What's interesting is that we can overectomize the animal, right? And take away the estrogen, the menopausal transition, or in humans is kind of like a similar situation. In animals, when we overectomize the animals, they now behave more like the males. Exercise does have an effect in attenuating weight regain after weight loss. And so we think that the sex steroids here, particularly estrogen, are really important in whatever's happening in females that allow them to sense that energy deficit and overfeed. We've done a lot of studies so far to figure out what's happening in females, and looking at things like leptin sensitivity. Is it the gut peptides? Are they differentially secreted? Neuroinflammation. We've looked at a number of things that don't explain the sex difference so far. So we're still on a search for what might be behind that.
Thank you so much for the detailed answer. I mean, so this is going to be your show for the next 10 years. Hopefully we can get, very good answer. No, but very, very exciting. I mean, it's exciting even recognizing this, this sex difference. We have other questions. Says, you mentioned palmitate and oleate. What other fatty acids do you have in the diets? Do you have evidence for interconversion?
Yeah, so we have only applied this technique to use fatty acids that are very common in the composition of the diet that we're doing. We're trying to reflect the fatty acids in the diet. Now, you could use different types of tracers and, to look at, are the saturated fatty acids behaving differently in this situation, or are the unsaturated fatty acids getting more oxidized, or are they the ones that are being retrafficked? We really haven't broken it down much beyond just trying to get some tracers in there that reflect the dietary fat that's in the food that we're feeding the animals. It's a really good question, and this type of approach with the right tracers, you could really parse that out and see what the different types of fats are contributing, or how they're being oxidized and stored in this context.
Yeah, thank you. There's another question. Here we have, so if you have any thoughts, comments on the idea that chronic exercise reduce the basic metabolic rate.
Yeah, reduces the metabolic rate. We haven't seen that in our animal models. If anything, exercise in our animal models that we have done, and I have to say, most of our exercising studies have been done in the weight reduced state, where metabolic rate is suppressed, right? So in that context, we have not really seen any negative effects of exercise on metabolic rate. We have seen very modest, maybe a calorie or two of an increase in metabolic rate, increase in metabolic rate in our animals in this context. But it's not huge, it's not significant. And the effect that we think we're having as the animals relapse and have to pay for the deposition of calories, that's a much more significant magnitude effect on the energy balance equation, we feel.
Thank you. We have another question about related, you mentioned something in your presentation about hormones. So if you can comment on the evidence on the exercise directly modulates ghrelin, leptin, PYY during weight regain.
Yeah, we had thought that, one of the hypotheses we had was that because exercise was allowing the animals to defend a lower body weight and a lower fat mass at the same leptin and insulin levels as a sedentary animal, we thought that exercise was affecting leptin sensitivity. And that's just, we've done some leptin sensitivities tests, and we've never been able to find evidence that that's what it's actually doing. There is some data in the literature that exercise potentiates GLP-1, PYY, and that response, that response, increasing those satiety signals to the brain, might be one mechanism whereby exercise is affecting appetite. I think the jury's still out, and I don't think that we're going to find one factor there. I think that exercise with its pleiotropic effects is going to affect a number of things that come back and affect appetite. But there is evidence for its effects on gut peptide in some clinical studies.
Thank you so much, Dr. Mclean. I think that we are more or less in time. So we're going to begin to close this section. We really want to thank you very, very much, Dr. Mclean, for providing us with your expertise, insight into metabolic science and obesity. It was really a fascinating talk, and the Q&A, I think, let us even with more hungry for more questions about more studies about this. Very, very exciting. In particular, I want to thank also Columbus Instrument for their support for APS Trainee Awards and activity, and as well as all of you in the audience for joining us today.
Yes,
finalize.
Thank you, Damien, for having me. Thanks, Chris from Columbus Instruments and Jacob from the APS. It's been a pleasure to be here.
No, well, really, really thank you. To you, Dr. Mclean and Columbus Instrument, for your science, your support. It was really an amazing session. And to all attendees, before you sign off, we hope that you will take a few minutes to complete a short survey about the session and your interest in future seminars. Thank you so much, and I hope all of you enjoyed the science today and will join us for future seminars. Thank you so much.